It's my great pleasure to introduce Kevin Best for his PhD defense. I am one of the co-advisors, Robert Gregg, along with Elliot Rouse. And just before I hand it over to Elliot, I just want to point out that when Kevin joined my group at Michigan, we had a wet lab as a temporary room, with really no testing equipment to speak of except for what we brought from Texas from my past job. And we had a lot of good ideas when I started with Kevin, but stuff wasn't really working until Kevin entered the picture, and now things are working, I'd say 99% of the time. And also working across multiple platforms, including commercial hardware, which is quite impressive, and you'll hear all about that soon. So yeah, anyway, it's a culmination of a large body of work that you're going to see today, and we're all very proud of Kevin's contributions. Yep.
Yeah, I just want to echo what Bobby said. It's been an absolute pleasure having Kevin in the lab. There isn't a project that he hasn't touched and impacted in some very serious way. So that's pretty cool. We don't see that very much. To have someone show up that can do it all and do it all well and with a good attitude and happy to be there. So Kevin will be missed, and it won't be the same without him. You guys are going to hear some very, very cool work.
It's not going anywhere.
That's true. Thanks. All right. Well, thank you both for the really kind words, and thanks everyone for being here today. It's really cool to see such a full house. I want to thank my committee for taking time out of their afternoon. Bobby, Elliot, Deanna, and Brent, thanks for being here and helping me review my work and present it well. So I want to start off motivating why we're interested in developing robotic prostheses. Most people use passive prostheses, which means that they can only resist motion. Advanced passive microprocessor knees, like this user's Autobot X3, can intelligently vary its resistance, but that's still all it can do. It can't create motion. This is like in your car if you only had a brake pedal and didn't have a gas pedal. And what this means for the user is that they have to compensate with their intact joints, which can lead to gait asymmetries, increased metabolic cost, overuse injuries, and overall less community engagement. So you can see this participant has to take much bigger steps with his right leg compared to his left, particularly on the ramp. And all passive prostheses, regardless of their complexity, are fundamentally limited. They cannot add energy into the system like biological muscles do, and so they cannot fully replace the functions of the missing limb. In contrast, the motors in robotic prostheses allow them to both resist and create motions. This is like having both the brake pedal and now a gas pedal. And so this helps the participant walk with a more symmetric gait. So you can see that when he gets to the ramp, he can climb with more equal step lengths on both his left and right legs compared to with his passive device. And there are many other potential benefits of this, including reduced energy usage and reduced strain on the intact limb. So if powered devices have these benefits, why do people still use passive ones? There are only 3 commercially available powered knee prostheses on the market, and none of them have much market share. And as far as I know, there are no combined powered knee ankle prostheses available for consumer use. And I'd argue that this is because developing a really effective robotic prosthesis is difficult. There are hardware challenges. It can't be too loud or too heavy. It has to fit inside pants. These are all real design challenges that are hard to achieve. There are economic challenges. You have to be able to design and manufacture them at prices that the market can afford. And there are also software challenges. It's hard to write control methods that robustly and effectively assist users throughout their day. And this final point is the fundamental problem that I've worked on during my PhD. How do you make these robotic prostheses do what the user wants at the right times in a way that's helpful? So in my talk today, I want to share 3 main ways that I've been working towards advancing robotic prosthesis control. In part 1, I'll walk you through the control methods we developed to more effectively control a robotic prosthesis while maintaining its clinical viability. And we'll talk about what that means and why it's important. In part 2, we'll look at clinical benefits and explore how the control methods that we developed in part 1 can bring tangible benefits to users. And then in part 3, we'll look at how these controllers respond to gait perturbations that could occur in real-world ambulation, and how the control choices we make affect the user's ability to withstand them. So we're going to start off with control development. You can think of the controller like the brain of the prosthesis. It makes decisions of what the motors should do, when, and how to do it. And we implement this controller in software. And at the end of the day, it comes down to some equation like this, where the motor torque tau is the output of some function f. And it's our job to choose this function f so that the leg behaves appropriately. Often our goal here is biomimicry. And what we mean by that is that we want the leg to behave as if it were a healthy biological limb. So this will be our North Star throughout this first part of the presentation. A traditional way to select F is to make the prosthesis joints behave like spring damper systems using an impedance control law. So it calculates the joint torque tau based on the current joint angle theta, the current joint velocity theta dot, and 3 tunable impedance parameters, the stiffness K, the damping B, and the equilibrium angle theta EQ. So to make the leg behave as desired, you change the values of these impedance parameters over time based on discrete gate events. Often these controllers need user-specific tuning, in which a clinician would watch the user walk, and they would tweak these values until the desired gait is observed. While this can work really well, and it can actually create fairly biomimetic behaviors, the ideal parameters depend on the activity, which means that many parameter sets and tuning sessions are potentially required if you want to get that optimal biomimetic performance across various tasks. And in a clinical setting, this would be pretty difficult, as it would take a lot of time, equipment, and engineering knowledge that a clinician might not have. And I would argue that relying on manual expert tuning to achieve biomimetic performance isn't clinically viable. And what I mean by that is if I went to the prosthetics and orthotics clinic and I said, hey, I have this great new device, but you have to add 3 to 5 hours to every fitting appointment so that we can make it work, they probably wouldn't be interested. So instead, what we want to do here is create an alternative framework that can still create these biomimetic behaviors, but without that manual tuning burden. So back in 2021, Emma Resnick collected a data set of able-bodied people walking at various speeds and inclines. And our general approach is to use this as demonstration data to construct a mathematical model of how people walk. Once this model is trained, we can use the sensor measurements from onboard the prosthesis, pass them through the model, and have it output the desired prosthesis behaviors. This way, we can rely on actual data to create our desired biomimicry without manual tuning. So what do I mean by behaviors? In this first work, we used a method that Kyle Embry had developed to model normative joint angles, also known as the kinematics. To control the prosthesis, we would simply take the output from this model, which may tell us that the knee should be nearly fully extended and the ankle should be slightly dorsiflexed, something like that. And we would use the motors to drive the leg to that configuration. So this is called position or kinematic control. And Kyle's model took 2 inputs. The first is a phase variable S, which estimates where the user is within the gait cycle. You can think of S as going between 0 and 100% completion of each stride. And during steady walking, it'll look like this sawtooth wave. Siavash Razazadeh showed us previously that we can calculate S based on the global orientation of the user's residual thigh, which has this sinusoidal shape during walking. If we divide this trajectory into 2 parts, a descending part on the left and an ascending part on the right, and we flip that descending part over the x-axis, we get something that resembles this phase variable. And what's nice about using a phase variable is that the user still has control of their thigh angle, which indirectly gives them control over the prosthesis. So this video, Bobby was talking about our wet lab. This is taken from that wet lab a bunch of years ago. It was still pandemic times. You can see the gloves that I'm wearing, but it shows how the phase variable works. So just by moving my thigh angle in different ways, I can either take steps forward or backward, and I'm in control of the prosthesis's progression. So the second input is a task variable, which we defined as the walking speed and the ground incline. And just like phase, we developed algorithms to estimate these online using sensors just from onboard the prosthesis. For time's sake, I'm going to skip over how they work, but I'm happy to talk about them later. So given these inputs, the model computes a weighted Fourier series where the different Fourier terms are dialed in and out based on the task variable. And Fourier series are a good fit here because they inherently capture the periodic nature of gait. So using some convex optimization to solve for these beta terms that parameterize the model, we can fit it to the joint angles in the data set, producing this continuous surface, that describes normative able-bodied joint angles and how they evolve across the gait cycle for different speeds and inclines. And then we can simply use like PID joint controllers to drive the prosthesis to those references. So we deployed this controller on the prosthesis and it worked fairly well. It could automatically detect and adapt to varying speeds and inclines and produce the appropriate behaviors. You can see how old these videos are because the floor around our treadmill wasn't finished yet. That's why I'm inside this kind of 2x4 fence. But while it mostly worked and we presented it at IROS, we did notice two problems that you might have picked up on. The first is the leg appears to pause right at toe off. You can see the knee and the ankle stop moving ever so briefly right when the foot comes off the ground. And this sudden deceleration didn't feel very good, nor was it biomimetic. Another issue is that the ground interaction wasn't quite right. So if you look closely at the foot during stance, you'll see the toes rise and then fall again, which creates a non-biomimetic ankle torque profile that is unsettling to walk on. So that's shown in green. So we tried to address these two limitations in our next work. The first problem, the joint angles pausing right at toe off, was due to how we calculated the phase variable. This spot in the middle where the thigh changes directions causes the phase variable to momentarily pause, which in turn stops the commanded joint angles from progressing. To fix this problem, we divided the gait cycle into more sections, and we used time to control the phase estimate progression during the portions of low thigh velocity. And what this did is it removed that pause in the phase trajectory, producing a signal that's more like that ideal sawtooth wave that we're looking for. To fix the non-biomimetic ground interaction and the ankle behavior, we switched from the kinematic control paradigm to an impedance control paradigm. And we did this during the stance phase because the spring damper behavior of an impedance controller allows the foot to better comply with the ground and create that natural behavior. So rather than controlling the joints to follow desired kinematic trajectories, we instead controlled their dynamics by modulating the stiffness, damping, and equilibrium angle. But to make this change, we needed something to replace the kinematic model. So rather than outputting desired joint angles, we need a new model that takes in gait phase and task, and instead gives us stiffness, damping, and equilibrium angle. Remember, these are the parameters that are typically hand-tuned in the traditional impedance control approach. This time, we chose to model them using a linear combination of polynomials. Since we're only modeling the stance phase, we don't need the model to be periodic. And we chose polynomials because they're good approximators of arbitrary functions, and their parameters enter linearly. So we again set up an optimization problem to find these X matrices that define the model, and to fit it so that our impedance controller produced the torques contained in the dataset. For those of you that are familiar with optimization, there were a few tricks that we had to do to ensure convexity. So we had to relax the model and treat this product term as its own independent polynomial. And then the fitting problem reduced to a convex quadratic program. If that didn't make sense, don't worry about it. So after we run this optimization, we get these equivalent models that describe how stiffness, damping, and equilibrium angle should evolve over the gait cycle to produce the right behaviors for different speeds and inclines. We again implemented the controller on a prosthesis and had a few participants try it out. You can see that our impedance parameters on the left are continuously evolving based on the estimated task and gait phase. And if I let this video run for a little while, you'll see that the treadmill will change speed and incline, and the prosthesis's behavior will adapt to match it. And compared to those kinematic control videos I showed you earlier, you can see that we fixed both the pause at toe off, as well as that ground interaction, so the toes are no longer wobbling. To show that we didn't lose any performance relative to the hand-tuned impedance control approach, we implemented both controllers and ran a series of experiments. We compared each controller on its biomimicry, which again means its ability to replicate normative able-bodied joint motions. So these plots show the average knee angle trajectory for various ground inclines under each controller. The bottom row shows the normative able-bodied trajectories from the dataset, so this is what we would like our prosthesis to produce. We compared the middle row, which are the results from the hand-tuned version, against the top row, which are the results from our new data-driven approach. When we compared it across both the knee and ankle, kinematics and kinetics, we found that our data-driven approach was as good as, if not better than, the hand-tuned approach of replicating normative able-bodied joint motions. And the key here is that it did it without requiring manual tuning, maintaining its clinical viability. So following these positive results, Kara and I then expanded this approach to sitting and standing from chairs of various heights. And then Ross and I applied the same framework to stair ascent and descent with similar positive results. So we're able to create these normative biomimetic joint patterns all by learning models based on able-bodied demonstration data instead of relying on manual tuning. So while our results were really promising, everything I've shown you so far was demonstrated using the same prosthesis. Leg 2, as our lab creatively calls it, is a device that was intentionally designed for easy control, but it also has other practical limitations of weight and bulk that may prevent the design from going home with someone. And if we want our controller to have actual real world impact, we need to show that it can generalize to other devices, and that its success isn't wholly reliant on this specific hardware design. I want to give a quick example to help motivate why these hardware properties might matter. One important property is the prosthesis's actuator inertia, which roughly speaking can be understood as its resistance to rotational acceleration. You're likely familiar with adaptive cruise control algorithms, which try to keep a fixed following distance between your car and the car in front of you. And let's say you wrote this algorithm and it works very well for this specific car. If I tried to directly use the same algorithm on a much heavier vehicle, you would likely have problems because it might not brake or accelerate hard enough. You'd likely need to consider this extra weight and modify your control algorithm to get the same performance. So for the same reasons, actuator inertia matters for prostheses. So leg 2 is specifically designed with minimal actuator inertia, which is part of the reason why it's so bulky and heavy. In schematic form, its dynamics look like this, where the main thing is just inertia and it's quite small. Other devices we use in the lab, such as the open source leg and the OSER Power Knee, are lighter and more compact, but that comes at the expense of potentially more complex drivetrain dynamics. So let's take a look inside the open source leg, which Senther and the OSL team created with specific design objectives that were different from those when leg 2 was created. The whole point of the OSL project is to accelerate research like my own by providing a common and accessible hardware platform to the field. This means that their design prioritized a low number of custom components, used off-the-shelf parts wherever possible to keep costs down. This makes the OSL easier to machine, assemble, and afford, but it also introduces some complexity to the drivetrain. So each joint here has its own actuator, and they're shown in this pale yellow color. These actuators have their own internal transmissions, which have their own dynamics. They drive an additional belt transmission that ultimately moves the joints. And it turns out when you load this belt, it stretches. So there's some kind of series elastic effect going on that we need to handle. So when we characterized and modeled the full OSL drivetrain, we found that its dynamics look a little bit more like this, with a bit more inertia, damping, and friction, and this variable stiffness series elastic actuator that we need to deal with. Luckily, we found that the same model does a really good job of describing the power needs dynamics. So if we develop a method to account for them, we can apply it on both systems. So put in equation form, we want the closed loop dynamics to follow this impedance behavior on the left. And our real dynamics look something like this, where we have belt springs, friction, damping, and inertia getting in the way. And don't worry about understanding these equations, just know that they're different. So Gray and I tackled this problem by developing a new method where we first select our motor command to cancel out the actuator's friction. When you do this, our closed loop dynamics reduce to this, leaving just damping, actuator inertia, and the spring to deal with. And you can note here that these dynamics are linear in the state variables, and linear dynamics are good because they allow us to apply tools from classical control theory. Particularly here, we're just going to use traditional pole placement techniques to shape our dynamics to get as close as possible to the desired behaviors. So if you're familiar with Bode plots here, our desired closed loop dynamics are shown in this dashed blue line, while our system's real dynamics are shown in green. And we can select our pole locations in our actuator state feedback controller to get as close as possible with our actual dynamics to that desired. So to validate our compensation method, we mounted the OSL ankle to a mechanical dynamometer, which you can see in the window actually right over there. which interacted with the joint and measured its torque response. We commanded different pairs of stiffness and damping to check to see what the dynamometer actually felt. And if the joint produced the impedance we commanded, we would get these straight lines back. We found that our compensation method was pretty effective in improving the OSL stiffness accuracy, with our results shown in purple compared to the uncompensated case in blue. While we saw some improvements in the damping accuracy, we didn't get as close as stiffness, as modeling and canceling friction in practice is really hard. Nonetheless, we were able to take the same control framework that we had developed on leg 2 and transfer it to these other 2 devices by accounting for their more complex drivetrain dynamics. So we can get the same behaviors across all 3 devices. Okay, so now that we had this controller running on these different devices, we wanted to look at how it could provide meaningful clinical benefits to users. So why do we care about clinical benefits? At the end of the day, insurers who pay for most prostheses are really only interested in new devices if you can show them that it'll improve someone's health and cost them less over the long term. And unfortunately, when these investigations have been done in the past, robotic legs haven't demonstrated strong benefits. Now, this could be due to the control limitations of traditional approaches that we talked about before, but it also may have to do with the tests we're performing, and there may be benefits that existing clinical tests don't capture. Most clinical tests are time-based and performed at a low exertion level, and we're curious to see what would happen if we increase this exertion level and look at more endurance-based metrics like step count or distance traveled. So we performed a case study where we asked an individual to complete up to 15 laps over our ambulation circuit as fast as he could. He repeated it 4 times, twice with his passive everyday prosthesis and twice with our robotic leg. Here's a quick speed up view of this test. You can see that he goes up the ramp, down the stairs, sits down, and goes back the way he came over and over again. And as expected, we didn't see a time improvement, with the robotic device in blue producing around the same average lap time as the passive device in pink. So if speed was our success metric here, this would again not be a positive result for robotic prostheses. Even if we look within each activity, because you may think, okay, going upstairs with a robotic prosthesis should at least be faster. We still didn't see that it was faster than the passive device in any of these cases. However, we did see that the participant was able to perform many more laps with a robotic device, showing that it did provide him with an endurance benefit and just not one that would be captured in standard clinical tests. So our research group has gone on to show quite a few ways that Leg 2 can provide clinical benefits over passive prostheses, and I've listed many of them here. However, this is an N=1 research device, and again, if we want to maximize our clinical impact, we have to show that we can produce similar results on a commercially available prosthesis, like the Össur Power Knee, because this could actually go home with someone. But the question is, if we translate the same control algorithm, will the clinical benefits follow? So to begin answering this question, we partnered with Össur, who sent us one of their power knees to reprogram with our control method. We ran a study involving repeated rapid sit stands, a repeated stand, walk, sit, shuttle test. And if you ever did the pacer test in elementary school, that's what inspired this test. And a fast 15-minute walk on the treadmill. And based on what we found in that case study, we made sure that each of these tasks was high intensity and would be fatiguing to try to leverage any benefits that might show up. So participants repeated this experiment under 3 conditions. The first was with their passive device. So for most participants, this was a passive microprocessor knee, but we did have one participant with a purely mechanical knee. The other condition was with the power knee, but using the factory default software. So if you were to buy the knee from Össur, this is how it would behave. And then finally, using the power knee, but with our custom control software. This video shows one of the participants performing the repeated sit-stand test under each condition, where passive is on the left, the power knee with the default controller is in the middle, and ours is on the right. This plot shows the ground reaction force asymmetry with our controller in teal and the default controller from Össur in purple. And these are both normalized to the passive condition. So lower is better here, with negative values, meaning that reduced the asymmetry compared to the passive condition. So the user is using both legs more equally with lower values. We observed that the power knee under both conditions improved this GRF symmetry, but with our controller, it created the largest effect. This plot likewise shows the average time required to complete a sit-stand cycle, again normalized to the passive condition. So lower values are better, as reduced cycle time means increased maintainable speed. And our control approach again increased the speed, where the default controller from the factory actually reduced the sit-stand speed. We likewise observed clinical benefits in walking. We saw that the power knee under both controllers elicited better biomimicry. So this plot here shows that we got increased ankle plantar flexion torque that's more similar to able body just by actuating the knee joint. We saw an increase in toe clearance, which is important for preventing tripping. And we saw a decrease in the peak hip flexion torque, which means that the user didn't have to work as hard to swing their prosthesis forward after each step. And in most of these metrics, we saw that the power knee helped in either case, but that our controller created the largest effect size. All right, next we gathered qualitative feedback from the participants about how they felt about these two controllers. And so here's one participant's thoughts on the power knee in general and how he thought it would improve his life. Hopefully the sound
Hands
works.
down, no doubt in my mind that especially if you're a more recent amputee, like mine's only been 5 years.
Yeah.
I'm kind of used to this one now. Having something like that would make my life so much easier. It's all of them, but that stand,
Yeah.
being able to stand up without using my hands, to have to push myself off or balance myself to get up out of a chair,
Yeah.
that it's phenomenal.
Okay.
It's absolutely phenomenal.
Sweet.
Walking, it doesn't take me as much energy to go as far as it would with this non-powered knee.
Right.
So I think over the long term, it's going to make me more active because I enjoy walking.
Yeah.
I enjoy moving around, but when it gets to the point where it's just too difficult for me to do, I'm not gonna hurt my body for it.
Yeah.
And I think that a power knee or something similar to that would be able to just be able to let me enjoy more.
So we do need to take qualitative feedback from participants like this with a little bit of a grain of salt, because people can sometimes be biased to enjoy the new devices, and they can try to please the researcher by telling us what they think we want to hear. But in this case, this participant, as well as one other participant in our study, actually went to their prosthetist following the study and asked to be switched to a power knee. So to me, that's very honest evidence that they felt like it was giving them at least some kind of benefit. Next, we're going to hear from one of our younger participants about how the controller improved his walking gait compared to how it was with the default power knee software.
And especially like with walking, I felt like once you could get into that good like rhythm of like a good gait, it felt very natural. I walked relatively recently, like a couple of years ago, with both legs, and it felt kind of like that natural like two-legged walking. So I would say like today I feel like when I was able to do it correctly, it kind of mirrored that in a sense, where I was able to walk like almost perfectly or like naturally.
So it's cool to hear his perspective and that he could feel some of these benefits that we're measuring about his gait, and he could internalize them. So yes, when we transferred the control algorithm to the power knee, we found that many of the same clinical benefits transferred as well, including some new ones that we hadn't seen before. The only one that we had yet to show is this increased ambulation endurance, and part of that was due to some overheating problems we had with the power knee hardware. So we're hopeful that in the future, with some clever experiment design, we could show this as well. We basically pushed the hardware harder than it was meant to go to compress the experiment into a lab-based session. So Bobby and I got to go to Iceland and present our results to the engineering and clinical teams at OSER, and we had a really great time. We even got to have one of their employees who tests a lot of their new devices walk around on it for a few hours and give us feedback, and he had some really great insights that were useful for us. We learned a lot, and this was one of the most fun experiences that I've had in grad school. Okay, so in this final part, we're going to talk about how the decisions we make from a control perspective influence the prosthesis' ability to handle unexpected gait perturbations. And why do we care about gait perturbations? Well, we often design and test our prosthesis controllers in only controlled nominal conditions. So like in a lab and on a treadmill like this. But when we send someone home, real life is messier and less structured. We often don't think about these kind of real world situations. We're tripping on an unexpected object or walking over uneven terrain need to be handled appropriately by the prosthesis. The human body can do this really well. And if our prostheses are going to be biomimetic, they should be able to also. To understand how a prosthesis would respond to these conditions, I need to introduce the concept of mechanical joint impedance. Mechanical impedance determines how perturbing motions imposed to the joint are opposed by changes in torque. So if I take this joint and I move it upwards, the impedance tells me how the prosthesis is going to resist that motion. And there are a few key facts about impedance that are helpful to know. The first is that from perturbation experiments like these, we know that humans exhibit consistent impedance patterns while walking. That is, when you perturb them, they have consistent torque responses. And this suggests that impedance likely performs an important functional purpose, and we may want to consider replicating it in our prostheses. Second, we know from our theoretical work that joint torque and impedance are independent. And that means we can specify both the nominal torques and its response to perturbations. And finally, we know that perturbations are required to observe impedance differences. So if you have two systems that have the same nominal torque behavior, you have to apply perturbations to be able to tell them apart. And I think an analogy is really helpful here. So imagine you're driving down the road in this old Cadillac, which has a really low impedance suspension. When you hit a bump, it'll be fairly forgiving. You might bounce a little bit, but it'll be pretty smooth. It'll definitely be different from if you hit that same bump in a sports car. This would be much rougher because it has a high impedance suspension. And when you're just driving down the road, you might not notice a difference between these two cars, but as soon as you hit a bump or a perturbation, you would be able to tell the difference. And prostheses are the same way. So let's say it was dark and you stepped on this bone that my dog Lila left out. The response would be very different in low versus high impedance conditions. A high impedance would cause a much greater change in your centroidal dynamics compared to a low impedance one. And while we know that these would be different, we don't know which one was necessarily better. So what we want to investigate is how the selected impedance affects someone's nominal gait, as well as their ability to withstand gait perturbations. So in an impedance controller, I know I'm using the word impedance a lot, I apologize. The impedance of an impedance controller is determined by its stiffness and damping. So by changing K and B in this controller, we can change its perturbation response. So we did a pilot study where we generated an array of different stiffness and damping behaviors to see how they affected the user's gait and their ability to withstand perturbations. We chose these different behaviors such that they span the space of possible impedances. So we have very low ones, very high ones, and various shapes. We also included the able body impedance behaviors that were identified in those perturbation experiments I showed you earlier. So that is condition A. We had a participant walk on each condition on a treadmill while we recorded their kinematics and the forces they created. We applied random surprise perturbations that simulated either slips at heel strike or slips at toe off by changing one of the bell speeds. So if you watch, it'll pop up and say perturbation. You can see either the foot stops or it accelerates quickly. In addition to quantitative measurements, we also asked the participant about his own perceptions of each condition. We confirmed our theoretical result that different impedance behaviors produced minimal differences during nominal unperturbed walking. So here I'm showing the kinematic and kinetic traces of the knee and the ankle, which are largely similar despite the big differences in impedance. So while we had previously shown that this should be true theoretically, this was the first time that we demonstrated it in hardware. During perturbations, however, the different control conditions created very different responses. So you'll see in this video of a push-off slip that on the prosthetic side, the conditions E and D on the right seem to have a more exaggerated response compared to A and B on the left. You'll notice D and E cause the participant to grab the handrail after the perturbation, and A and B don't. So I'll play this a few times because I know it's a lot to look at. So here we're looking at a stability metric called whole body angular momentum. And the human body tries to keep angular momentum low when walking, which is why when you slip, you throw your arms up. You're trying to cancel out that increase in momentum. The average nominal values are shown in red. So these are the angular momentum during just regular walking strides with no perturbation, versus blue is immediately following the perturbation. What I want you to notice is that it appears that the lower impedance conditions, A and F, did a better job at regulating momentum compared to the high impedance conditions, as they showed the smallest differences between the nominal and the perturbed strides. Further, you can see that they're the most similar to what the participant's biological limb did when it was perturbed. However, when we asked the participant how he felt about each condition, he consistently rated the higher impedance conditions, so C through E, better than the low impedance ones. So even though A and F appeared to reject the perturbations better visually and scored better in terms of stability metrics, the participant disliked them compared to the higher impedances. So this was just an initial pilot study for this project, and we need to perform more analysis and have more participants to make any strong claims, but we do have some initial takeaways. First, we showed that different impedances can have minimal effects on the nominal kinematics and kinetics. And this confirms our prior theoretical results. Second, we showed that impedance has strong effects on the user's perturbation response in terms of kinematics, kinetics, and common stability metrics. And this highlights that impedance is an important property that should be considered when designing a robotic prosthesis that could experience perturbations in the real world. Finally, we saw that the user had strong, consistent preferences regarding the impedance choice, and that his preferences didn't necessarily align with the conditions that maximized our stability metric. But to this last point, it's important to note that it's really difficult to define, quantify, and measure walking stability, and there's a lot of future research that needs done here to fully understand this discrepancy. So just as a final recap of what we talked about today, we started by developing a new control algorithm that enabled biomimetic behaviors across different tasks while still maintaining clinical viability. Then we developed the control theory necessary to deploy this controller on additional prostheses with more complex drivetrain dynamics, broadening our potential for clinical impact. We investigated the ways in which our control methods could bring tangible benefits to users' daily lives. And we're continuing this partnership, and after graduation, I'll be working with OSER on ways to integrate our control approach with their existing products to hopefully bring these benefits into their mainstream clinical practice. And finally, we looked at what joint mechanical impedance is and why it matters. And this case study provided the foundation for future research that will hopefully make prostheses better at handling perturbations and make them better equipped for the real world. Lastly, I just want to share what is probably my favorite video from grad school. We were showing off some of the features of face-based control, trying to get OSER excited about it. And Andrew almost killed Brenda's very expensive camera. So we've gotten a lot of mileage out of this video, and it's excellent. All right, so on to acknowledgments. First, I want to thank my funding sources, without which I wouldn't have been able to complete this dissertation. I was mainly funded through the Graduate Research Fellowship program from the NSF, but I also received support from the NIH and from OSER. So thank you for putting food on my table and letting me do this really fun work for a job. I also want to thank all of the co-authors who I've gotten to write these papers with. I've been incredibly lucky to work with such a talented and hardworking group of people, and I'm really proud of what we've been able to do together. I want to thank the entire NeuroLoco family for being such a wonderful group to work with. And being here for 5 years, one picture isn't enough to kind of capture everybody. So these are taken from various times throughout my time of just wonderful people and fun times that we've had together. So thanks for making my grad school experience so much fun and for being such a wonderful community. A lot of credit for that community is due to this dynamic duo. So Bobby and Elliot, I want to thank you for cultivating this wonderful research environment. I appreciate all the guidance, mentorship, teaching, and trust that you've given me over the years. You've helped me become a stronger engineer, a more effective communicator, a better leader. So thanks for all the time and effort you put in. I also want to acknowledge another dynamic duo from Notre Dame who have been influential mentors of mine for quite a few years. Sorry. They were the first to introduce me to the worlds of robotics and to biomechanics, and they provided me with really good career advice when I needed it. Jim in particular had some really wise advice when I was looking at grad schools, and I was like, I don't know if I want to leave Colorado. Like, it's really nice here. And Jim said, don't be stupid, apply to Michigan. So Jim, thanks for the advice, and I'm very glad I took it. Beyond career advice, Jim's research has directly influenced my own. He and others like Eric Westervelt and Jesse Grizzle pioneered this idea of using a phase variable to control gait in a robot. And this has been instrumental in making our control algorithms work on prostheses. So it's just cool to see kind of how research builds on each other and how you never know where your research is going to go. I also want to acknowledge all the people who make robotics here run. Denise, Dan, Damon, Kimberly, Christina, David. I'm sure there's someone I'm forgetting, but thank you for all that you've done for me and all that you do to make this student experience here so amazing. To all my friends outside the lab, I wasn't gonna cry. I'm not gonna cry. I'm very grateful for you and for all the fun that we've had together. Many of you are either here in person or on the Zoom call. And I really appreciate all the support. All of you, whether you're here in Ann Arbor or far away, you enrich my life, and I'm very grateful for you. Lucy, thanks for being by my side and balancing me and for all the wonderful adventures we've had together. I had more written, but I'm excited to keep going. Thanks for the tissues. Yeah. Lastly, I have the best family in the world, no pun intended. You guys support me and love me, and I love you back, and I'm very blessed to have you in my life. All right, feelings are over. Time for Q&A.
Hey, Kevin. Awesome work. So I had I guess, broad overarching question. So you developed these controllers, put on people across a lot of hardware, and especially in your second aim showed like it improved a bunch of metrics that you cared about, right? And you're saying you're going to work on commercially using it. So I guess the broad question I'm asking is like, what's the gap in research left, right? Like, is it solved? Like, do we put like biological controllers and impedance and, it's just about putting them and it's just an engineering challenge, or are there fundamental problems with this method that, still need to be solved?
Yeah, I think so. Certainly it's not solved. And I think the big thing that what we're missing right now is some kind of volitional control. So, right, everything, we're assuming that you're going upstairs, or you have some way to detect you're going upstairs, but we still don't have a good way of like, kneeling down and tying your shoe or playing with your kid or things like that. So, right, a lot of the things we were doing are just for the regular ambulation modes that we consider, but there's still a long way to go to where it feels like a part of the body and where you can control it for arbitrary things. And I think that's where the next research frontier is. I think there's a way to combine kind of ways of reading the body with EMG or kind of however you want to do that and supplement that with this. So you have your kind of automatic behaviors that happen that you don't think about, right? Like when you walk, you don't think about it. And I think that's where our research will fit in. But there's also going to be somewhere where the person has control, and that's kind of the next place.
I would just add that while Kevin's right, he's being modest. He did solve the kneeling down and tying the shoe thing.
That's true.
We have a video of that.
Very nice work. I'm kind of curious on your thoughts of what is the role or the potential role of like machine learning and artificial intelligence in this space and like the future of prosthetics and AI? Is that like where the field is going or should be going? And what's your take on that?
Yeah, I almost made a slide where it was like, we have GPUs, why are we doing this, right? Everything is solved by RL, parallelization, and simulation-based kind of controllers. I think the biggest hurdle right now is we don't have a good way to simulate the human. And that's like, you know, Ellie and I can argue about this, wherever Ellie is. But simulating the human and being able to do a good predictive model of what they're going to do that kind of RL training, I think is a huge barrier. So I'm not saying it's not possible, but I think that it kind of, if you miss a piece in that simulation environment, what are you really learning? So maybe someday, but for now, I think this is the way to go.
Thanks.
No rebuttal.
I was gonna say, you can respond to that, Ellie?
Great talk, Kevin. Besides stability, do you have any other areas of prosthetics research that you think impedance is going to have an implication in the real world?
Ooh, that's a good question. I mean, so you've seen kind of our ideas of thinking that impedance is really just this kind of partial derivative thing, right? And I think user preference is going to have a big part of that. We saw it in this research where, because there's not all those signals that you get back, like a biological limb has very good sensors. You get a lot of information back. And right now, you know, prostheses don't feed all that information back, and so there's maybe something with preference and impedance that's important to consider in addition to stability. And then maybe if you could reconnect some of those pathways, that might change.
So we have a question from Varun on Zoom. So, hi Kevin, congrats. Question, perturbations off a treadmill have one massive difference. Off a treadmill have one massive difference. The option to change speeds and even to stop. Do you have any insights on how an impedance controller would work in these situations?
Yeah, that's a really good question, Varun. Part of, like, I would add to your question is that we only showed what are called phase shifting perturbations. And so it either accelerated or decelerated the gait cycle. And there's a whole class of perturbations that are outside of that. We could go out of plane, we could do things where, you know, you allow the user to stop. And so I think, you know, I'll punt the question and just say, yes, we should consider those as well. And I think impedance is relevant in all of those things.
Thank you, Kevin. Very good presentation. So yeah, I have a pretty quick question regarding like user preference and maybe a good metric. So as you've shown, like in the perturbation study, like some controllers, they are more robust with respect to like perturbation, but meanwhile, seems like users, they don't, you know, really prefer those controllers. And I know there's also some debates on like whether we really should create something biomimetic or, you know, just, you know, maybe it's biomimetic, but maybe users, they don't like it. So what do you think about this one? How do you determine which metric is the most important one?
Yeah, so maybe to rephrase your question is, should we listen to users and do what they like versus what we say they should like? And I think it's a little bit of eating your vegetables, right? Like there are some things where I know if I make the leg behave this way, it will be better for you in the long term. But there's also the other side of that argument of, if you don't like it at all and you don't use it, like then I can't control that. You're gonna go home and you're just gonna use something different. So I think there's a middle ground there. We have to consider what users like. But at the end of the day, we also do know from science and kind of engineering standpoints what is good for them. And so maybe that's education to say this is what is good for you, and so it might be worth this discomfort. I don't know, but I think it's a middle ground.
I have a quick question. So you looked at whole body angular momentum in one of your studies. Mm-hmm. Do you think it's possible to estimate that using just sensors on the leg and maybe close the feedback loop around that somehow? Because you used the whole gait lab setup to estimate that, right?
Yeah. My quick answer would be no, because right, my example was hands matter, right?
Yeah.
But I do think there are ways, I mean, Ryan would argue this. I think, well, having sensors only on the prosthesis are really good. there are probably minimally invasive ways that we could add that extra information. So, right, I'm wearing a watch that can measure accelerations right now. It wouldn't be that hard to have that stream to the prosthesis, and that's not a huge quality of life detriment to the person. So maybe there's a way that we could add and kind of sense that.
So you're saying arm motion contributes substantially to whole body angular momentum.
Totally, yeah. Did you have a question still, Mohammed? Mohammed, behind you. Bobby, back there.
Oh, sorry.
I'll make it pretty quick. Great talk, Kevin. I feel so proud that I've shared office space with you for 3 years. I had a quick question. I think you sort of hid it under the rug. Maybe don't talk about it. At some point, your controller took as an input the task thing.
Yeah.
So I was interested, are you trying to explicitly, with your controller, estimate what is the task? Is it a continuous space? Is it a discrete set of tasks? Are you estimating it like a Kalman filter type stuff? Or can you talk more about it?
Sure, good questions. So it is a continuous space. So that's kind of the key to those models is they're not discretized. So we can measure real values. It's nothing fancy, as fancy as a Kalman filter. We're just doing things like moving averages. We have kind of gone down that Kalman filter route, but it went towards adding complexity for no real payoff, so we kind of went back. Can you remind me what else was in your question? Yeah, so we explicitly do measure it though. So we do want it, like the controller has an output that says the incline was this. And I think there's an argument here, again, Ryan and I can debate this, on the value of that, because it helps in the engineering context of saying, oh, it thought it was, -3 degrees and it was really -10 degrees, and I can do something to fix that. Where if I kind of lump everything together and I don't explicitly have those outputs, I can't know how to fix it. I don't know, that's just one argument for having it be kind of cascaded like that. Laksh again.
Maybe last question?
Sure.
So I want to talk about, sort of what you talked about at the end of your slide, right? Like you worked on like these labs that worked on like robots, and now you're working on robotic legs that are for humans, I guess. Yeah. So I was wondering, since you've got experience on both ends, like what are sort of the differences, or can you like make the same leg for a robot and a human, both from a design perspective, but also on the controls perspective? And is there something we can learn from that field, or they can learn from us?
Sure, yeah, I think, so I won't speak to the design side because that's other people. But from the control side, there are two kind of big differences, and it has to do with how much you can sense about the system and how much you can control. So in a robot, you have access to all the information. Whereas on the prosthesis, kind of what Bobby was just asking, we only know things local to the prosthesis unless we add sensors. But bigger than that, in a robot, you know your goal, right? So I know there's some central controller in a robot that says I'm walking upstairs or something. In prosthesis land, we're always kind of guessing, right? We're building a tool that's supposed to figure out what the person wants and do that, but we never have access to that true information. So I think those are a huge difference between fully autonomous robots and robots that people wear or use as a tool. But there are definitely things that we can learn and pass between them, right? Things like the phase variable, also things I already kind of argued against using RL for prosthesis control, but I think there's so much success in quadrupeds and bipeds with that there's got to be something useful there that we can take.
Okay, so at this point, the committee will meet privately with Kevin, but why don't we thank him one more time for his great presentation.